Hey everyone and welcome. Have you ever really looked at something simple like a salt crystal or a piece of glass and just wondered what is going on deep inside? Well, today we're going to pull back the curtain on the secret architecture of solids. We're diving into that invisible world of atoms that gives everyday materials all their amazing and, sometimes really surprising properties. And this brings us right to the central mystery we're tackling today. Why is it that some solids, like say a quartz crystal, are so geometrically perfect, while others, like a chunk of plastic, just seem, totally random? What is the fundamental difference that makes them behave in such completely different ways?
So just take a look at this. On the surface, these are two crystalline solids that look pretty different. On the left, you've got this absolutely stunning blue vitriol crystal with these razor-sharp defined faces. And on the right, good old table salt. Now, even though they both have an ordered internal structure, their appearance really begs the question, what is this hidden architecture that defines them? And what happens when that perfect order is missing entirely?
And that, right there, is the core theme for today. It's this fundamental battle that's happening at the atomic level inside every single solid you see. It's a constant struggle between perfect, repeating order and total, frozen chaos.
You see, a solid's internal structure pretty much falls into one of two major camps. On one side, you've got the crystalline solids. These are the champions of order. Their atoms are arranged in this beautiful, repeating three-dimensional pattern. But on the other side, you have the amorphous solids, the agents of chaos. Their particles are just all jumbled up, totally random, with no pattern whatsoever. It's almost like a liquid that was flash frozen in a single instant. So, let's start by exploring that highly organized and, frankly, incredibly structured world of the crystalline family. This is where we find nature's most perfect patterns. Okay, so what does that phrase, long-range ordered structure, actually mean? Well, imagine you have this intricate wallpaper pattern that repeats perfectly. Now imagine it repeats not just across a wall, but up, down, forward, and backward, filling the entire volume of the solid. That is a crystalline solid. This perfect internal order is exactly what gives them their unique and often beautiful external shapes. So how does nature build something so perfectly ordered? It all starts with a fundamental blueprint called the unit cell. Think of it as the absolute smallest piece of the crystal that still contains the full repeating pattern. A Rubik's Cube is the perfect analogy here. The entire cube is like the crystal, and each individual colored block, that's the unit cell. You just take that single unit cell and stack it over and over and over again in all three dimensions, and boom! You've built the entire crystal structure. It's really that simple and that elegant.
Okay, now this is where it gets even more interesting, because it turns out not all crystals are created equal. The crystalline family is actually divided into 4 distinct clans, and what defines each one is the kind of chemical glue, the bond, that's holding their particles together.
First up, we've got the ionic clan. This includes our friend table salt, NaCl. Here, you've got positively and negatively charged ions, and they're held together by pure electrostatic attraction. It's like a rigid grid of tiny, powerful magnets. Now, this strong attraction makes them hard and gives them really high melting points, but it also makes them brittle. If you try to shift the layers, suddenly the like charges align, they repel each other, and the whole crystal just shatters. Next is the covalent network clan. These are the true heavyweights of the solid world, things like diamond and quartz. In these, every single atom is locked to its neighbors by incredibly strong covalent bonds, forming this massive, continuous network. It's less like a stack of blocks and more like one single giant molecule. Or think of it as an unbreakable three-dimensional jungle gym made of atoms. Then we have the molecular clan, like ice or dry ice. The particles here are individual molecules, like H2O. Now, while the bonds inside each little water molecule are strong, the forces holding one molecule to another are super weak. They're kind of like a crowd of people just loosely holding hands. And this is what makes them soft and gives them low melting points, because it just doesn't take much energy to pull them apart. And finally, we have the totally fascinating metallic clan. We're talking copper, gold, iron. This structure is really unique. You've got a fixed grid of positive metal ions, but their outer electrons, well, they aren't tied to any single atom. Instead, they form this free-flowing sea of electrons that just moves through the entire crystal. This electron sea is the flexible glue holding it all together, and it is the secret to why metals can conduct electricity and bend without breaking. This table just lays it all out perfectly. You can really see how the forces directly predict the properties. Those powerful electrostatic forces in ionic crystals, they make them hard but brittle. The super strong covalent bonds in a covalent network solid, that leads to extreme hardness. But check out the metallic column. Those free-flowing electrons from the metallic bonds make them the only group that's a good conductor of electricity. It's a perfect summary of how that atomic structure defines everything for our 4 crystalline clans.
All right, we've spent plenty of time in the neat and tidy world of order. So now, let's jump back to the other side of our story, the unpredictable and really fascinating world of the amorphous or non-crystalline solids. You know, the word amorphous literally means without form, and that is a perfect description. Their particles are completely disordered. They're often called supercooled liquids, which is such a great way to think about them. Just imagine you could freeze a liquid so fast that its molecules had zero time to arrange themselves into a neat crystal. The result would be an amorphous solid, a perfect snapshot of liquid chaos frozen in time.
And this chaotic structure gives them some really unique traits. Of course, there's that random particle arrangement. They also don't have a sharp melting point like a crystal. Instead, they just get softer and softer over a range of temperatures. And they're isotropic, which just means their properties are the same no matter which direction you measure them. Makes sense, right? In a random jumble, every direction looks pretty much the same.
And you are surrounded by these materials every single day. Glass, plastic, rubber, even tar. These are all proud members of the amorphous club. They're the true rebels of the solid world.
So, we get to the crucial point. Why does any of this invisible world of atomic order and chaos actually matter? How does it affect the materials we see and touch and use every single day?
This is the perfect example of that connection. So why is a diamond the hardest natural material known to man? It's all down to its internal structure. It's a covalent network crystal where every single carbon atom is locked into a rigid 3D web by incredibly strong bonds. To scratch a diamond, you have to physically break those powerful bonds, and that is just extremely difficult to do.
On the flip side, why can you bend a metal wire without it snapping? Again, it's the structure. That sea of mobile electrons in a metallic crystal acts like a flexible glue. When you apply force, layers of metal ions can actually slide past one another. But that electron sea just flows around them, constantly holding everything together. That is what makes metals malleable.
There's this one idea about covalent network solids that I think is so powerful. The entire crystal is a single molecule. Just think about that. That one sentence perfectly captures just how interconnected and strong this structure really is. It's not just a collection of particles, it's one massive unified thing.
So the next time you look at a glass window, a metal fork, or a plastic bottle, you'll know the secret story that's being told at the atomic level. Is it a story of perfect order? Or is it one of frozen chaos? Their secret is their structure, and now you know how to read it. Thanks for joining me.